Well, good afternoon to my physical science class. Today we're going to talk about a topic related to pressure, and that's called Archimedes' principle. People who were in class on Tuesday, we did some ideas related to something called Bernoulli's principle, which said that if I've got a faster moving fluid, there's less pressure. Today we're going to talk about Archimedes' principle, and all these topics we're going to be talking about relate to the idea of pressure. And pressure is force divided by area. So let's take this situation. An aircraft carrier, which is going to be a significant part of our military, weighs 97,000 tons, and a ton is 2,000 pounds. And this aircraft carrier is made up of iron on its outside, and the iron itself has a density of 8 times that of water. And yet, aircraft carriers are designed to float. Okay, so if it weighs so much, if it has so much weight, and the density of this iron is 8 times more dense than water, if I took a cannonball that was made of iron and tossed it in the water, it would sink. Why is it that this aircraft carrier floats? And that is because of Archimedes' principle. So if we were to define Archimedes' principle, we need to talk about the idea of buoyancy. And if you could, make sure you have your notebook out and your pencil out and get ready to take this. You can pause the video if needed, but there are a couple key points we're going to make here. So buoyancy is the upward force exerted by a fluid on a submerged object. Doesn't matter what the submerged object is, the fluid that object is placed in will exert an upward force. It doesn't matter what the weight of the object is, the fluid will exert an upward force. And as a result, objects appear to lose weight as a result of this. Okay? Now, in this case, the buoyant force equals the weight of the fluid displaced. And that, in a nutshell, is Archimedes' principle in bold, if you want to label that as such. The buoyant force upward equals the weight of the fluid displaced. Okay, so let's take a look at an example of this, and we're going to run through this a couple of times. Now, those of you who were at a distance yesterday, you will kind of understand this. And as I go deeper in a fluid, the pressure increases. And as a result, the net force is to kind of push upward on something. If there's more pressure here and less pressure here and less pressure here, the net result is to kind of try to push something up. That's that buoyant force. So let's say I have this yellow object here. And this yellow object has a weight of 20 newtons, let's say, in air. Okay? And let's say that I take this yellow object and I place it in this water here. It still has a weight of 20 newtons. Okay? And that's not going to change. That's its weight. It still has 20 newtons trying to push down. But now let's say that this water that has been shoved out of the way here, let's say that that has a weight of, I don't know, let's say it has a weight of 5 newtons. Okay? So what does Archimedes' principle say? The buoyant force equals the weight of the fluid displaced. So if that's the case, if this water weighs 5 newtons that got pushed out of the way here, that means that there's a buoyant force acting up on this object of 5 newtons. These two values are equal. The weight of the water displaced equals 5 newtons, which means that in water here, this object would not weigh 20 newtons. It would weigh 20 minus 5. It would weigh 15 newtons. Okay? That because of that buoyant force there. So here's what I want you to look at. Here you have this block. It has a mass of 7 kilograms. We know mass isn't weight, but we'll kind of approximate that. That'll work. And then when I plunge this into water, now I can measure this amount of water that spills out, and the amount of water that spills out has a mass of 3 kilograms, which means that the difference between this 7 kilograms of this weight, again, kilograms is not a weight, it's a mass, and this 3 kilograms pushing up means that this scale will read 4 kilograms. Okay? So let's take a look at this. An object weighs 100 newtons in land. I'm going to take this object, I'm going to put it into the water over here. When I do so, it's displacing, let's say that it's displacing 80 newtons of water. That this water that's been shoved off to the side equals 80 newtons. Its weight is not changing. Its weight is still 100 newtons. But now, if this is 100 newtons, or I'm sorry, the weight is still 100 newtons. If it is shoving 80 newtons of water out of the way, call it H2O, then the buoyant force upward is 80 newtons. And as a result, this object will appear to weigh in water 20 newtons, because the difference between the weight and the buoyant force equals the weight of this object in water. But you and I know that not all objects sink. Okay? Some objects float. So let's say I take this object right here and I put it into this water, and it only comes to this point. It floats at this point. And let's say again that this object has a weight of 100 newtons when it's over here. But now it floats. So if it floats, that means that this weight of 100 newtons, there's no net force here. It's not going anywhere. That means that the buoyant force here has to also equal 100 newtons. These two have to be equal. Otherwise, this object would either accelerate up or accelerate down. What this means is that this weight of this water, guess what? The buoyant force equals the weight of the displaced fluid. So here's what we've got. That means that this weight right here, if we were to take this amount right there, that crosshatch right there of water that's been pushed out of the way, the weight of that would equal 100 newtons, because that is my buoyant force. This weight of this water that's been pushed out of the way equals 100 newtons. So here we have this simulation, which will help show this. Here's a brick. It has a mass of 5 kilograms, so if I multiply that by 9.8, it has a weight of 49 newtons. Okay, I'm going to take this on a scale just to show you this. This does have a weight of 49 newtons. Now notice this blue arrow that is on the brick. That represents the downward force of this 49 newtons. So if I toss this brick into water, it'll obviously sink. But you'll notice that the amount of water it displaces equals 24.5 newtons. So if I were to have a chunk of water that was this big, it would weigh 24.5 newtons, and as a result, there's 24.5 newtons of buoyant force. So the difference between my weight of the brick, which is 49 newtons, and the buoyant force, which is 24.5 newtons, if I put it on a scale in water, you'll notice that it weighs now 24.5 newtons in water. It weighs less in water because the difference between its weight and the buoyant force, 49 minus 24.5, equals 24.5 newtons. Let's get this out of here. Here we have a larger wooden block. Okay? Now this wooden block has the same weight as this brick, but it takes up more volume because it's less dense. But you'll notice it still weighs 49 newtons. But if I toss this into water, you'll notice that it floats. Okay? And the reason why it floats is because the buoyant force upward and the weight of the block itself are equal and opposite. What this means is that this amount of water that's underneath the water line, guess what its weight would be if I were to have put that water on a scale? its weight would equal 49 newtons. The buoyant force equals the weight of the water displaced. And in fact, watch what happens. If I put this brick in water, it will sink. But if I put it on top of this wood block, you'll notice now that I have 49 newtons and 49 newtons. That's 98 newtons. This whole system still floats because now this amount of liquid equals 98 newtons of weight. So going back to our initial situation, the reason why this water carrier floats is because the amount of this ship that is underneath the ocean, the weight of the water that's pushed off to the side because of that, equals the whole 97,000 tons of the aircraft carrier. What's beneath the water line is 97,000 tons of water that have been pushed out of the way, and so that's going to exert a buoyant force. They're going to be equal and opposite here. Okay? Now, I have an ice cube, or an iceberg, I should say. What does this tell us? It tells us that the weight of this iceberg equals the buoyant force provided. So the amount of water that's displaced here underneath the water line equals the weight of the iceberg itself. Now here's the curious thing. When ice melts, ice is less dense than water, it would melt into this volume because ice is made of water. When it melts, this amount of ice would melt perfectly into that amount of water there. Now the reason why balloons float, it doesn't matter if it's a hot air balloon or a helium balloon, is because of the same concept. Okay? What happens is that this volume of air that's moved off to the side is going to weigh more than the weight of whatever is in here. Maybe this is helium, which is less dense than air, which is why it would weigh less for the same amount of volume. Maybe it's hot air inside here versus cold air. Hot air would be less dense, so it would weigh less for the same volume than regular cold air, which is why hot air balloons float. Now sometimes if you go to salt water is more dense than regular fresh water. So if I push that water out of the way, it's going to exert more of a buoyant force because you're actually displacing more weight. So this happens to be the Dead Sea, which happens to be a very, very salty lake. So it's very, very dense water. And since the human body is made of water as well, you'll notice that you are incredibly buoyant in here because there's more of a buoyant force provided by this salt water than there would be otherwise. Now on the side of some ships, you'll notice these lines. And the reasons why they have these lines is because these ships travel in different densities of water, and they are going to rise and sink because of Archimedes' principle. In tropical freshwater, that's what TF means. Okay? That means that you're going to sink more into the water, and because you have to displace more water to get the same buoyant force. If you have winter water is going to be cold water. Cold water is more dense. It's going to provide more of a buoyant force, so you can submerge less of that water to get the same buoyant force. So, attached to your lesson for today, I just have a few short questions related to Archimedes' principle and seeing if you understand what we're talking about today. And if you could, make sure you complete that and submit that. We'll show that this works in class through lab situation. And other than that, I hope you have a good Wednesday. We will talk to you later.